Great. Welcome, everyone. Thank you very much for joining us today. This is Ehsan Sudman from Julius Wolf Institute at Charité University Medicine in Berlin. I am also a member of Education and Student Committee of European Society of Biomechanics, ESB, and I will be your host today. This webinar is the first episode of ESB Webinar Series organized by a student committee, and we are aiming at covering applicable topics in the field of biomechanics in both research and industry. Rodrigo Romarovsky, Enrico Dallara, the head of the student committee, and I are responsible for organizing these webinar series. Unfortunately, Rodrigo is not present today since he's busy in Japan participating in CMB conference. So now I would like to hand over the webinar to Enrico to explain a little bit more about the European Society of Biomechanics and its activity. Enrico, please.
So thanks a lot, Hassan. So hello, everybody. My name is Enrico Dallara, and I'm from the Insegno Institute for In Silico Medicine in Sheffield, United Kingdom. And at the moment, I chair the Education and Student Committee of the European Society of Biomechanics. So I'd like just to steal 1 minute from our speaker to introduce this webinar series. So this is the first webinar of, I hope, a long series to introduce different open source toolkits available in our community. So the main target of these webinars are ESB student members, but of course not only. So also other members are welcome to attend. If you are not a member of the ESB yet, please take a look at the chat on the right-hand side. And we're put there all the different links that you can follow to look at the opportunity to apply for becoming an ESB member. So I would like really to thank a lot Ehsan and Rodrigo for the great work that they've done to organize this first event. And of course, the colleagues from SimVascular for delivering this seminar. So I leave the mic back to Ehsan, who now will introduce the speaker. And I hope that you enjoy the first webinar.
Great, thanks, Enrico. So back to the topic of our first webinar. We are introducing SimVascular, a fully open source software package providing a complete pipeline from medical image data segmentation to patient-specific blood flow simulation and analysis. So the presentation will be given by Mr. Gabriel Maher. Gabriel is a PhD student at Cardiovascular Biomechanics Computation Lab at Stanford University, and his research is focused on deep learning for cardiovascular medical imaging, and he is one of the core developers of SimVascular project. The webinar will be 45 minutes, and it will then followed by 15 minutes Q&A session. So please take the chance and type your question in the comment area at the right side of the screen. And the question you are raising up now, we will address them at the end of our presentation. Now I would like to hand over the talk to Gabriel, and I hope you enjoy the webinar.
All right, great. Well, thank you very much, guys, for the introduction, and thank you, of course, to the ESB, to Enrico, Rodrigo, and Ehsan for putting this great webinar series together. As I mentioned, my name's Gabriel. I'm doing my PhD here at Stanford University, machine learning for cardiovascular imaging. Yeah, I'm one of the core developers of SimVascular. So my lab maintains the open source project SimVascular, which is the software we use for the research we do. And it's also used by other labs that do similar research. And namely, that research is on doing patient-specific cardiovascular blood flow simulations. So what that means exactly is that SimVascular is a software that will let you go through all the steps that are normally needed when you are performing these numerical simulations. So things like geometry generation, mesh generation, doing the actual simulations. That's all provided in SimVascular. And since it's open source, of course, it's available to anyone for free. So that's one of the great things about it. So in this webinar, I'm going to explain a little bit about what SimVascular is exactly, and then walk you through a typical demo project of the things you can do in SimVascular, so you guys can get a good idea of what's possible. Okay, so first things first, this is the website for SimVascular. It's simvascular.github.io or simvascular.org will also take you to the same place. And this is really the first place you can go to get more information about the project, right? So we can see that it tells you what it is, that you can do image data segmentation and blood flow simulations. And additionally, you can navigate the website to see, examples of what you can do. So for example, here's an image of a blood flow simulation in an aortic geometry for a particular patient. And so, you can see the video here, the streamlines are computed. And this was all done using SimVascular. So everything from generating the geometry of the blood vessels to making the numerical mesh to calculating or running the simulation to calculate the streamlines. And, so there's more examples. For example, here's a patient with a shunt. And so you can see that the blood flow was calculated in this geometry as well. Additionally, you can go here to figure out how to download SimVascular. So there's download links, and of course, since SimVascular is open source, you can even go to the GitHub repository that we have. So if you click on the source code repository, it'll take you to GitHub, and you can actually even find the code and look through the code and understand exactly how it's all put together if that's interesting to you. And yeah, the license is a BSD license, so you're free to use it for whatever purposes you like. Additionally, we have all our documentation of SimVascular here. So everything from how to install, guides on doing the modeling, the meshing, simulations, etc., and even clinical study cases that you can use to get an example of what you can do. Right. So for example, if we click the quick guide, it'll take you over here to the quick guide of how to use SimVascular, and in particular, on the left-hand side, you can download a demo project with all the files, so you can get started really easily. So yeah, so if you're interested in SimVascular, take a look at the website simvascular.github.io, and that will tell you everything you need to know about how to get started with it. Next, we have another website, simtk.org. If you go to simtk.org/project/SimVascular, it will take you here. And this is kind of like our support website. So this is where the downloads are. So you can go here to download SimVascular. You can download our simulation solver if you want to use that, and some of the other software we have. And in particular, there's also a forum that you can go to. And here you can post your questions if you run into issues, or if you need help, or if you have suggestions. You can post them here and let us know, and then the SimVascular development team is actively monitoring this forum to help you solve any issues or questions you might have. All right, so remember those two things: our SimVascular website and simtk.org, and those are really the essential things you need to get started. Great. So now I'll go into a demo of SimVascular to show you the main features. And then after that, we can go to questions on that you might have. Okay, so SimVascular is really built for a particular workflow when doing your patient-specific cardiovascular simulations, right? So what that means is we have a particular patient for which we have, say, medical image data, and we want to run a blood flow simulation of what the blood flow looks like for this particular patient's blood vessels, right? And so that means that for our fluid dynamic simulation, we need a mesh that accurately represents the geometry for this particular patient. And so to build those things requires a number of steps. And so these are the steps that have been put into SimVascular to make this process easier for you. So right here, I have a list of the different steps, just so that you can get an overview before we get started, so you know what to expect. But generally, the way this works is that you have your image data, usually a 3D MRI or a CT image, so that you can see what the patient's blood vessels look like. And the first step you do after loading in the images is that you want to construct the blood vessels. And so the first step for that is that you will indicate in SimVascular the blood vessel path lines, simply by clicking the points where the blood vessels flow. Once you have the blood vessel path lines, you can then start constructing the blood vessel surface by creating these 2D contours around the path lines. And you do that for every vessel. And then once you've done that for every vessel, SimVascular can create a smooth 3D surface that will combine all the vessels into one model. And this is done, of course, so that you can then generate a mesh, a finite element mesh, which can be used for numerical simulations. And then once you have this mesh, you can then run the simulations within SimVascular, and then you can analyze the results and get any output data that you want from the simulation. All right, so generally speaking, whenever you use SimVascular, it's going to be this process, right? The blood vessel center lines, to the 2D segmentation step to create the surface, to the 3D model, to the mesh, to the simulation. All right. Okay, so just remember that when we go through SimVascular. Okay. So here's the SimVascular software. This is the main screen you'll see when you first launch SimVascular. It's sort of the home screen. And it doesn't show anything yet because we still need to load in data, right? And so the way that works is we click File, we create a project to organize our data. And so we'll just call this webinar demo, right? Okay. And so once we've created the new project, you'll see that the left menu populates with a number of categories. And this is the area where all the data that you create and all the files that you create while working with SimVascular will be organized so that you can go through and inspect them when you need to. Okay, so as I mentioned, the first step with any SimVascular project is, of course, we want to load in the patient's image data so that we can see what we're working with. And so the way that works is we go to the SimVascular Data Manager menu, we right-click on Images, and we choose Add or Replace an Image. And then it will open up a file browser, so you can browse to the area where you have your image. So I'll do that here. So here I have the sample data that we have on the SimVascular website. You can choose whether you actually want to copy the file. Sometimes images are large, so you may not want to copy it, but sometimes you want to keep it organized and copy it into the project. And you can also decide whether you want to scale the units. So for example, if you want to go from centimeters to millimeters, but for now we'll just leave that as it is. And then you can give it a name. All right, and once you go through all those steps, you'll see that now the views we were looking at have been populated with the image data. And so for those of you that are familiar with, say, medical imaging or the way that the conventional way that doctors look at these images, you'll recognize these views. The reason is that normally medical professionals look at 3D images by considering a number of different views, and these have their own corresponding names, and so we have those in SimVascular as well. So the sagittal view is a view from the side of the patient, and the axial view is a view you would get if you were looking from the bottom to the top of the patient's feet, say. So this shows you sort of a cross-section through their body. And then the coronal view is the view you would get if you were standing in front of the patient and just looking straight at them. So you would see their right-hand side would be on your left and their left-hand side would be on your right. So those are just a few things to keep aware of when you are looking at these views. Additionally, we also have the 3D view where you can, sort of pan the image around to get a better idea of it. If you move your mouse into any of these screens, you can scroll up or down to move through different slices of the image, and you further explore what your image data looks like. So this is definitely one of the handiest features of SimVascular, is that you can actually interactively explore an image and understand exactly what the geometry of the blood vessels looks like. All right, some other things we can do with the image is if you go to the Data Manager and you double click on the image, a menu will pop up, and this lets us actually do volume rendering. So volume rendering means that we can start to see what the 3D structure of the blood vessels looks like. So if we click volume rendering, we can indicate what pixel values we actually want to be considered in the rendering. And so usually, since we're interested in the blood vessels, what we can do is we can go to one of these other views here, and we can click, And if we then look in the bottom right corner, we can see information about the pixels at those points. And so in particular here, we can see pixel value 153. And so if we keep our eye on the bottom right corner and move our mouse around more, we can get a feel for what the range of the pixel values is that are in the blood vessels, right? So here it looks like something like, you know, say 60 to 170 is the range of pixel values we could see in the blood vessels. And so ideally, for our volume rendering, we want to keep that same range. So here we have, for the volume rendering, the pixel value histogram. And so these dots indicate the range that we're considering, where if we move them up, it indicates that we want the volume rendering to give a bright color to those pixels. If we move it down, we want them to be excluded. We can also click to add a new range to the volume rendering, and then we can use that to sort of further refine things. Right. Okay. So as I said, we want to have a range from say 50 to 170. So we can move that one about here. And so in the upper end of the range, we want the values to be bright, so we move that up. And then here we close off the range at say 170. And so yeah, as you can see here, we currently can see much more of the 3D structure of the vessels. We can click this button here to enlarge the view. Right. And so yeah, so using this we can see more of what the 3D structure is, and of course we can we can refine this to get a better idea, right? So yeah, so see, refining it a bit, we get a better idea. And if we click here, we can turn off the panels, so we can really see, actually in 3D, what does it look like? So here we get a pretty, good view of the blood vessels and the kidneys, and we can see what those look like. All right, so the volume rendering is a bit compute intensive, so I'm going to turn that off as we continue. Turn the crosshair back on, and go back to the 4-panel view. Great. So yeah, as I mentioned at the first part, the next step we want to do to make the cardiovascular or the patient-specific model is to start constructing the vessel path lines. All right. So to do that, we move to the left here to the data manager. We right-click on paths, and we choose Create Path. You can give the path a name, and so usually you would name it for the vessel that you want to do. So in this case, we're going to first construct the aorta, and so that's I'll call it the aorta, and click OK. And now we'll see that that path has been populated in the data manager. So if you double-click on it, the path planning menu opens up, and there's nothing there yet because now we need to start adding path points. And so the way to add path points is to navigate to the image views and to control-click the areas that you want to add a path point. So essentially, in doing this, you are looking through the image, and you are telling SimVascular the locations where the vessel goes through. So we'll start with the aorta, and we'll start from the top. So I'm going to just navigate to the top of the aorta, say somewhere like here. And now I have a good view of the cross-section of the aorta. I can start adding these path points, right? So I can add one here, right? So I control-click, and the first one appears. I can then scroll down a bit more, add another one, and scroll down some more, etc. And doing this, we can trace the vessel path and really make sure that we get the exact geometry that we want. You have full control in this process, so you can really go through and trace the geometry in as much detail as you want. If you only need a core simulation, you can do a few points, and if you want a very accurate path line, then that's possible too. You can simply add more. Okay, so we added our path points, and so now if you look in the 3D view, you can see the trajectory the path is traced, and you can see that we kind of were able to trace the geometry fairly well, right? And so we would have to do this for every vessel that we wanted to simulate. So here we have the aorta, and say we were interested in one of these vessels down here, one of the iliac arteries. We would have to create a new path and start doing that one as well. But in the interest of time, I'm just going to import some pre-made paths that I have already so that we can go to the next step, which is the segmentation step. So I'll just import the paths. Okay, yeah, so as you can see, I imported the paths, and now they are populated in the render window. Okay, great. So yeah, so once you have the paths, the next step is to construct the vessel surface. And so the way that works is that we create a segmentation group. And so to do that, we right-click on segmentations, we choose create contour group, we give it a group name. And so as I mentioned, every contour group corresponds to a specific vessel path. And so you have to select which one you want to segment. So here we'll do the aorta. And if you leave the name blank, it will just give it the same name as the path, which is fine in this case. So we get a segmentation now that says aorta. Great. So we can double click on the aorta to open up the segmentation menu. And as you'll notice, now the view has changed because now we have entered into the segmentation view, which is something that was specifically built for SimVascular to make this process easier for people doing these segmentations. So essentially what you see in this view is we have a planar view of the cross-section of the vessel corresponding to a plane that's perpendicular to the current vessel path line, right? Because this really lets us see what is the cross-section of the blood vessel at this particular path point. And so this is what's shown here. So you can really see the surface of the blood vessel and what its shape is. And then in this view, we have a gradient image to additionally help you identify where the boundaries of the vessel are, because those are usually high gradient sections. So in the segmentation menu, what you can do is you can drag this slider to slide across the vessel, right? And so doing this, you can see how the vessel evolves as you move down the path line, right? And so this is the tool that you would use to really go through and construct the surface of the vessel and make sure that you've got any, specific areas that you're particularly interested in. For example, if there's maybe an aneurysm or a stenosis, you can really go through using the slider and make sure that you accurately capture the geometry for those locations. But in particular, you have to create the vessel model, you use this view to construct surfaces at intervals so that we can create an accurate 3D surface, right? So I'll show how that works for a few different options. All right, so first of all, probably one of the simplest ones is the spline polygon, which essentially just lets you draw the vessel surface yourself. So it's the most manual, but it gives you the most control. And so the way that works is you click the spline polygon button, you then move to the 2D view of the vessel cross-section, and then you can just simply indicate the surface of the vessel by clicking points, and it will iteratively refine a B-spline to capture the vessel surface, and you can double-click to finish it. And then, of course, you can adjust if you want to, refine your vessel surface by clicking on the points. And yeah, that will get you your first segmentation, right? And so if we zoom in here, right, we can see that we have created the vessel surface at that location. And so to finish the 3D surface for this vessel, we would do this as intervals. So we would move, slightly further down the vessel. Now we could keep drawing using the spline polygon to make the surface, but I'll show you another method, which is the threshold method. So the way to use the threshold method is you click it once, and it will open the threshold menu, and then you click it again, which will activate the threshold. Then you go to the 2D view, and you left-click, and then if you drag up or down, you can adjust the pixel value threshold you want to use for the segmentation. So the threshold will look for all pixel values within a certain range and then find the boundary of those pixels and use that to compute the segmentation, right? So it looks here like about a value of 80 seems to be about good, right? So that gets us the next segmentation. Additionally, we could use a, well, let me actually explain a few more of the individual segmentation steps. So we have more methods, things like you can draw a circle or an ellipse. And in fact, one of the most recently added aspects is machine learning. So if we click the machine learning, it'll activate it for you, which takes a moment as it needs to load the machine learning models, which you can view the progress by looking in the console window to see what it's doing. And once it's done loading those models, you can then use the machine learning to compute segmentations automatically without sort of manual interaction. So this can be good if you have to do a lot of segmentations that you don't want to get fatigued. All right, so I think it's ready. So yeah, so now that we clicked it once, so it's activated. So we can click it again, and yeah, you see without any interaction from us, it was able to compute the segmentation using a neural network. So if we wanted to do more, we could do more of those. Right, we just move along and we click the areas that we want to compute more segmentations. Okay, so computing segmentations individually is great if you want to have full control over the geometry. What you can also do is use batch mode, which lets you do multiple locations at the same time. So if you click batch mode in this area, you can enter the locations that you want to do more segmentations. So for example, I could do 150, 180, 210, 220, and say 250. And then if I click on the corresponding segmentation method, it will go through and do those locations for me, right? So you see here, I got the segmentations for the method I was using, right? And so I can go through and I can see what they look like to make sure that they're okay. So yeah, so the batch mode is definitely useful if you want to do lots of segmentations for a particular vessel. And in particular, recently added is, in fact, you can even do segmentations now for multiple paths at the same time, and this will use the machine learning method to do that for you. So in the segmentation window, if you click multi-vessel path, you can select the paths you want to segment. So we can select here the aorta and the right iliac. We indicate the frequency along the paths that we want to do segmentations. And we can also indicate the number of Fourier modes we want to use, which is a smoothing technique. It will calculate a Fourier transform of the segmentation and remove any high frequency modes. So here we indicate that we want only the 3 lowest modes, so that will give us smooth segmentations. We then click segment using machine learning. It'll ask us for a name to give to the segmentations that it's about to generate. So let's say, ML for machine learning. We click OK, and we can follow the progress in the console window. And so here we see that it's busy segmenting the aorta. And so we have to just wait for that to finish. Takes about a second per segmentation. And then once it's done with the aorta, it'll go on to the next vessel, and then we'll be able to see the segmentations after it's done. Okay, so it started segmenting the next vessel. We'll wait a minute for it to finish. Okay, great. So yeah, it finished. And so as you can see, let me turn off one of the old segmentation I was doing. So as you can see, we were able to almost automatically segment the vessels we were working with all at once without having to do anything. And so we can actually double click on one of them to expect them. You can click in the contour list and you can walk through to make sure that if there were any that need to be more accurate, that you can go through and improve those or change those. Okay, so that's more or less how the segmentation works, right? So you would do this for every vessel that you want to have in your model. Again, in the interest of time, I'll load some pre-made segmentations that I had, so that we can move on to the next step, which is to create the 3D model for our patient-specific simulation. Oh, so here I have the segmentations that I created earlier. All right, so for the 3D modeling step, we now take our segmentations and turn those into a 3D surface, a unified 3D surface. So to do that, we right-click on models, we choose Create Model, give it a name. Again, let's call it Webinar Model or something. Okay, we then double-click on it, and the modeling menu will open up for us. So this menu gives us the options to create models and then to refine them after we've created them. So we can click the button here, Create Model. This will allow us to select the segmentation groups we want to use. So in this case, I'll select the two that I used. But if I had many paths or many vessels, I could select different subsets depending on what I wanted to study. But in this case, I only have two, so I'll just use those two. And then we click OK. And SimVascular will start combining those together and creating the 3D surface. So if I open the 3D view a bit more, we can see the 3D model. I'll turn off the slices. Great. Turn off the segmentation as well. Okay, so here we see the 3D model that was created from our vessels. And so as you can see, it's all been combined into one model. Additionally, SimVascular will also compute what aspects of the model are a wall. So for example, here, and what aspects of the model are a cap, which is not needed for the boundary conditions, right? And so, yeah, so these are all merged together, and these can then be used to create the mesh later. In particular, we can now smooth up any areas of the model that still need to be refined, or we can repair any aspects that didn't come out the way we wanted. So for example, usually at vessel junctions, as you can see here, the model can be a little bit unsmooth. And so what we can do is we can use some local smoothing to make that better. So if we go to local ops, we can go to constraint smoothing, which will smooth the model while preserving the volume. We can click sphere to indicate the region of interest, right? So we can move that to the vessel junction, and then we can click smoothing. We can choose the number of iterations we want to run, for example, and then we click smoothing. And so as you can see, it now looks a little bit better, all right? So especially for avoiding things like numerical artifacts, it's good to make sure to inspect some of these regions and make sure that we smooth things properly. Okay, and so there are other operations you can do, such as global smoothing. But again, in the interest of time, I will just preload a different 3D model that I had generated already. Okay, so here's my 3D model. Looks almost the same as the one we just had. Great. So now once we have the 3D model, we can create a numerical mesh for our simulations. And so to do that, we right-click on meshes and choose Create Mesh. You can choose the 3D model that you want to use for the mesh. In this case, we only have one. And if you leave the name blank, it will just use the same name as the model. So that's fine in this case. And so now we end up with our demo mesh here. So we can left-click on that to open up the mesh menu. And this will give us the options to create the mesh we want to use. So in particular for the mesh, one of the things we need to do is indicate what element size we want to use. And so we can either enter that ourselves, or we can let SimVascular estimate it for us. And there are some advanced options, but I'll mostly cover the basics right now. So for example, if I click Estimate, SimVascular will estimate a mesh size that I need to make sure that the mesh has a decent quality. And so in that case, that's about 0.2. And so if I click Run Mesher now, it will create the mesh for the model. And so that can, depending on how many elements you have or how, what your mesh size is and how big your model is, that can take a while. But I think here it should finish relatively quickly. Yeah, so we just have to wait for it to finish. And once it's finished, it'll give you the mesh statistics, such as the number of nodes, the number of elements, the number of edges, and the number of faces. And so you can use that to get an idea of, what kind of numerical simulation you're about to run. And yeah, so this is the mesh. And if I turn off the model, I can move in and inspect it, so I can see what the elements look like, and go in and make sure that they're all okay. So I can look at the area that we just smoothed, and make sure that that came out fine, that there's no bad elements anywhere, which is useful to make sure that you have good quality simulations at the end. We can also look at the the caps and make sure that those are also okay. So yeah, this looks like it came out well. Okay, so now that we have our mesh, we can conduct a simulation, which is the final aspect that we're sort of interested in. So again, in the interest of time, I made a coarser mesh just so that we don't have to wait a long time for the simulation to run. So I'll just import that. Or actually, I'll just create a mesh with a larger element size. Okay, so here we have a coarser mesh, so that we won't have to wait so long, because I am just running this on my laptop right now. Okay, so now we can right-click on the simulation menu, choose Add Simulation, and then we can enter a name for the simulation here. So we can just call it Demo Simulation. All right, and then if we double-click on it, the simulation menu will open up. So the first tab you see is for the basic parameters of these simulations, such as the fluid density and the fluid viscosity. So those have been preset to typical values for blood flow simulations. But if you wanted to run different different types of simulations, you could edit those here. The next thing we can do is specify the inlet and the outlet boundary conditions. So usually those are things like either we specify a velocity, or we can specify things like a resistance boundary condition or other types of boundary conditions. And so what we'll do here is we'll specify an inlet boundary condition of the velocity at the top of the aorta, and then we'll specify resistance boundary conditions at the bottom, so that we can calculate the flow in that scenario. So the way to do that is to you double click on it, you choose the type of boundary condition you want to do, then you right click and you choose Set Boundary Conditions. So for prescribed velocity boundary conditions, we can prescribe the shape of the velocity profile, and then also how it changes over the course of the simulation. And the way we do that is we can specify the number of points to use in the profile estimation, and then we can use a flow file to indicate the the flow over the entire simulation. And so what that looks like, if I browse to the simulation directory, I can show you what one of those files looks like. And how to create these files is explained in the tutorials on the SimVascular website. And so here, I just have a simple flow file which specifies the flow at the start and at the end. And I've specified those to be -100. So -100 indicates that the flow is moving down. And so this essentially is just indicating a constant flow over the entire simulation. But there's definitely the possibility to specify different types of flows. And so you can look at the website to see how to do that exactly. I'll also just use one Fourier mode, use 2 points, and select the flow file that I have. All right, and then click OK. Great. So now we have our prescribed velocity boundary conditions set. We can now prescribe the resistance. So I double click again, I choose resistance, and then I right click and choose set BC. So you can choose resistance value. So let's just say something like 1,000. And these are just the typical units. Okay. So here we have our boundary conditions, and now we can move on to the rest of the simulation. So within blood flow simulations, you can choose between, do you want to keep the walls rigid or do you want them to be deformable, and what kind of deformability you want. So those are also available within SimVascular. So here we'll just choose rigid since it's the simplest. And then we can move on to the solver parameters. And so here you can choose things like the number of time steps, the time step size, some other more advanced parameters like we have backflow stabilization to ensure that the simulation doesn't diverge due to too much backflow. And then there are some nonlinear solver parameters as well as linear ones. And so these are advanced, and you can read more about how to set those on the SimVascular website. Typically, they're set to be, to work well for most simulations. So if you're just getting started, you probably don't need to edit these, but the information is there if you wanted. So here we'll just set the number of time steps, and in this case, I'll just use a relatively small number just so that we can see what it's like. I use time step size, let's say 0.1, and so you need to make sure that your time step size is sufficiently small for the stability of your simulation. And then we can set the number of time steps between restarts, which is a parameter used by the simulation by the solver to make sure that the accuracy stays okay. And so we can just set that to something like, say, 5. Okay. Then once we have those parameters set, we can move to the actual creation of the simulation files. So we choose the mesh we want to run. In this case, we only have one. We click Create Data Files for Simulation. All right, it will create the files, and these will be stored in your project folder. Then we can choose the number of processors to use for the simulation. So if you have MPI installed, you can use multiple processes, but it's also fine if you don't. You can just use one. And then we can choose the starting step number to be 0. And then we click Run Simulation. Okay, yeah, so if you don't have MPI installed and you choose Use MPI, it'll give you an error. So you may need to turn that off. But okay, so I just ran the simulation and it finished. And so we can, inspect the details to make sure that everything was okay. All right, it'll tell you things like the number of iterations it used, something, things about the residual, etc. So you can expect that to make sure that it was that it's doing what you wanted it to. Okay. And so once we're done running our simulation, what you can do is export the simulation files to a particular directory. So I have that set here to the, well, actually I can browse to where the, so the location of my SimVascular project file. And I can just select the demo simulation, that's fine. We can choose the steps to export. So we did 10 time steps. So I'll just choose to do that and export every step. We can choose what we want to export, and you can choose the simulation units. All right, so we click Convert, and then we click Open, and SimVascular will convert the simulation files for us. All right, so now we have successfully completed our simulation. The output files are stored in VTK accessible formats. So it'll store them as a polydata or an unstructured mesh, and so you can read those with any file, any program that can read those. We typically use ParaView, which is also a free and open source software. So if you wanted to use that, you could use it too. So I will just show you what that looks like. And in particular, these files will show us the results of the simulation and the output quantities. Okay, so ParaView is open. I can now navigate to the location of the simulation that I saved. And this will be in the it should be. Let me see, where did I export it to? Okay, well, it seems like maybe I exported it to a different location, so let me look for a second. Okay, so here it is. Yeah, so once we exported, we should have a folder that shows that says converted results. So we open that, and here are the results. And so you can open the one that you want to. So let's open the one for the final time step, and then we can view it. And so here we see the pressure in the vessel during our simulation. So, as you expect, since we started with a prescribed velocity, we have a high pressure at the top and a low pressure at the bottom, indicating that the flow moves to the bottom. And we can click here to view other aspects. So, for example, we can look at the wall shear stress, which is an important quantity in cardiovascular blood flow simulations. And this will show us the distribution of the wall shear stress across our geometry. And we can look at other things such as the traction, etc. And then this is how you would compute or investigate your blood flow simulation results. And then you could also use this to compute other things such as streamlines, and that would let you study the blood flow for the specific patient that you did. Great. So that was, in a nutshell, or in a lightning nutshell, the workflow for SimVascular. So we loaded our image, created the blood vessel paths, made the segmentations, then made a 3D surface, made a mesh for it, and then using that mesh, we ran a simulation, and then we viewed our results, which, as I mentioned, that's the SimVascular workflow. And so this is the, what SimVascular has made easier for you, and it lets you do all of that in one location. And again, all of this is explained on the SimVascular website. There's more examples of different, cases you can run through. So definitely make sure to check that out if you're interested. And, if you run into issues, you can go to simtk.org and look for SimVascular. And here you can download the software and the solver, and you can also find the forum if you have any questions. And great, yeah, so that was the end of the webinar. I hope you enjoyed it. And so now I'll pass the microphone back to Ihsan to answer questions and to wrap things up.
Great. Thank you very much, Gabriel. So we have still 10 minutes time. So I think some of the question has overlapped with your presentation. So I just mentioned the question, and then you can add information if you need it's necessary. So the first question was about using machine learning for segmentation. So do you want to add something to this question?
Yeah, so I think we walked through that. So as you saw in the in the software, there's three ways you can use machine learning. You can use it for a single cross section along the vessel center line. or you can do the batch mode for an entire vessel, or if you want, SimVascular has added the functionality to use machine learning to segment multiple vessels, and so those are all the machine learning options that are currently available.
Great. So there was the two questions, so I combined them in one about vein architecture and reconstruction. So they ask about what is the best way to reconstruct the vein structure regarding to the images? Is it possible with CT images, or it's also possible with DICOM images?
Yeah, so I think you guys should have a good idea of how that's possible now. So SimVascular can read most medical image formats like DICOM, MHA, CT, all that stuff. So you should be able to just take the image you have of the patient you're looking at and load that into SimVascular. And then as far as reconstructing the venous geometry, that would proceed like the workflow I just showed you, where you would indicate the center lines of the veins and then start constructing the surfaces and make the final 3D model. So yeah, that should all be possible within SimVascular.
Good, great. So the other question was about reconstruction of venous structure using CT images. So is it also possible to do that with SimVascular?
Yeah, so that depends a bit on what you mean about the venous structure. If you're talking about making a 3D model of the veins and their connection to each other, yeah, that's possible. You would just make the vessel surfaces, and then when you make a 3D model, it would put them all together. And so you could use that 3D model then to investigate the structure of the venous system, which would let you sort of explore that.
Great. And there was a question about exporting 3D geometry from the software. So in which files you can export the geometry? So which kind of file type you can export?
Yeah, that's a good question. So yeah, as far as exporting, that's definitely possible. So what you could do is just go to the software, and in the data manager, if you click on your 3D model and you right click, there's an option to export solid model, and the formats we export are VTK formats like VTP or VTK or VTU, but we also support STL formats. So those are the formats you could use to export the model.
Okay, great. And one last question I've just seen is, have you ever reconstructed vascular structure within an organ parenchyma?
Sorry, what was the last part?
So the reconstruction of vascular structure within the organ parenchyma or something, if I pronounce it well.
Okay. Yeah, again, SimVascular is not, the nice thing is that it's not limited to a particular, anatomy or geometry, right? If you have the image of the organ and the vessels are visible, you can simply load it into SimVascular and use the process I showed to, construct the vessels that you are interested in. So in that sense, yeah, you could use it to reconstruct the vessel structure around certain organs, as long as they are visible within the image.
Mm-hmm. Great. And the last question, I think, is about downloading the SimVascular. So do they need to register for downloading the software, or they can download it without any registration?
Yeah, you do. So our software is hosted on SimTK, at least the precompiled installers. So yeah, so to download it, you would need to go to SimTK and register, which is free, and then you can just download it from there. But if you want to download the software and build it yourself, you can go to GitHub, and so then you wouldn't have to register with SimTK. Well, you would still need a GitHub account, but yeah, those are the two methods with which to download the software.
Okay, great. And maybe the last question, so the questions are coming now.
Okay.
And maybe as a last question, Yang asked about can we import a model from CATIA or ANSYS inside the SimVascular?
Yep, that's definitely possible. I believe the formats we support for importing are, these VTK formats like VTP and VTK or VTU or STL. So if you have one of those formats, you can just, create a project, right-click on models, and then choose, import solid model.
Mm-hmm.
Yeah.
Great, good. Thank you very much, Gabriel. So we are perfectly in time. And so we will send you an evaluation form. Please fill it up and to help us to organize our webinar series based on your expectation. And please don't forget to subscribe to our channel. And I will add the ESB student committee email and the SimVascular email later on in the description of this video for those who are watching this video later on the YouTube. So if you have any questions, please don't hesitate to contact us. And thank you very much for joining us. Gabriel, do you want to add something as a last word?
No, thank you very much for tuning into the webinar. I hope you enjoyed learning about SimVascular. And yeah, as you know, we have a forum. So if you have any other questions, feel free to post those there, and we can do our best to answer those.
Good, great. Thank you very much, all. I hope you enjoyed the webinar, and we hope to see you again all in our future webinars. Thank you very much. Have a nice time. Bye.